Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 26 of the course Marine Renewable Energy Systems Design, Analysis, Design and Development. I am Dr. Basangowda I. Patil, Assistant Professor at Pandit Deen Dayal Energy University, Gandhinagar, Gujarat. In the previous lectures, we discussed the fundamental principles of wave energy converters, including wave resource characterization, numerical modeling approaches, frequency domain and time domain analysis, and the preliminary design parameters governing wave energy converter performance. Having understood how wave energy devices interact with ocean waves, we now move to one of the most critical subsystems of any wave energy converter, the power takeoff system, commonly referred to as the PTO. The PTO serves as the energy conversion interface between the mechanical motion generated by waves and the useful electrical power delivered to the grid or to an energy storage system. In many cases, the overall efficiency and economic viability of a wave energy converter depend strongly on the design and performance of its PTO system. In this lecture, we will develop a broad understanding of different PTO technologies used in wave energy applications. We will discuss their working principles, major classifications, operating mechanisms, advantages, limitations, and suitability for different wave energy converter configurations. This lecture will provide the foundation for the subsequent lectures where individual PTO systems such as mechanical PTOs, hydraulic PTOs, and direct drive electrical PTOs will be discussed in detail. So, let us begin our discussion on the overview of the power takeoff systems for wave energy converters. Having introduced to the concept of power takeoff systems, let us now understand why they are so important in wave energy conversion. As we know, ocean waves contain significant amount of both kinetic and potential energy, and this energy is continuously generated by wind action over the ocean surface and represents one of the most promising form of renewable energy available today. Wave energy converters or WECs are designed to capture a portion of this available wave energy. Depending on the device type, the absorbed energy may appear as the heaving motion of the floating body or the oscillation of a column or the relative motion between connected structures or the movement of a hinged mechanism. However, the energy captured by a WEC is initially in the form of a mechanical motion. Mechanical motion alone has practical value, alone has not practical value unless it can be converted into electrical energy that can be utilized by consumers, stored in batteries or supplied to the electrical grid. This is where the power takeoff system plays a critical role. The PTO acts as the energy conversion interface between the hydrodynamic subsystem and the electrical subsystem of a wave energy converter. In simple terms, the PTO receives the mechanical energy extracted from the waves and transforms it into useful electrical power. The importance of the PTO becomes evident when we consider the overall energy conversion chain. Even if a wave energy converter is capable of absorbing a large amount of wave energy, poor PTO performance can significantly reduce the final electrical power output. Therefore, the effectiveness of the entire wave energy system depends not only on the hydrodynamic energy capture, but also on how efficiently the PTO converts that captured energy. In practice, the PTO systems perform several important functions. They convert mechanical motion into electricity, regulate power flow, control damping applied to the WEC, and help maximize energy extraction under varying sea states. For this reason, PTO design is often regarded as one of the most challenging and important aspects of wave energy converter development. As highlighted by Falco and several other researchers, the overall efficiency of a wave energy converter is strongly dependent on the performance of its PTO system. Consequently, significant research efforts worldwide have focused on developing efficient, reliable, and cost-effective PTO technologies. Let us now look at why power takeoff system is often referred to as the heart of a wave energy converter. The figure here on the slide illustrates the complete energy conversion pathway. The process begins with the energy available in the ocean waves. Then these waves interact with the structure of the wave energy interact with the wave energy converter through what we call wave structure interaction. During this interaction, a portion of the incident wave energy is absorbed by the device. As a result of this interaction, the wave energy converter experiences mechanical motion. Depending on the device type, this may be heave, surge, pitch, oscillation of an internal body, or relative motion between two connected structures. At this stage, the energy still exists in mechanical form only. To make it useful for practical applications, this mechanical energy must be converted into electrical energy. This conversion is performed by the power takeoff system. The PTO therefore acts as a central link between the hydrodynamic subsystem and the electrical subsystem. Without the PTO, even a highly efficient wave energy absorber cannot produce usable electricity. For this reason, hydrodynamic performance alone is not sufficient when evaluating the wave energy converter. A device may exhibit large motions in waves, but unless the PTO can efficiently extract and convert that motion into electrical power, the overall system performance will remain poor. In addition to energy conversion, the PTO influences several critical aspects of wave energy converter operation. First, it determines the amount of power extraction that can be achieved from incoming waves. Second, many PTO systems provide energy smoothing, reducing fluctuations in power output caused by irregular or random sea states. Third, the PTO has a direct impact on the overall efficiency of the wave energy converter because losses can occur during mechanical, hydraulic and electrical conversion processes. So, efficiency is very important. So, finally, the PTO contributes significantly to the availability of the device during extreme wave events. The PTO may be used to limit excessive motions, protect components from the overload and improve operational safety, which highlights survivability. Therefore, while the hydrodynamic design captures wave energy, it is the PTO that ultimately determines how effectively the energy is transformed into useful electricity. This is why many researchers describe the PTO as the heart of a wave energy converter. In fact, a large proportion of modern WEC research focuses on improving PTO efficiency, reliability, controllability and long-term offshore performance. Having understood the central role of the PTO system, we can now proceed to examine different PTO technologies that have been developed for wave energy applications. Types before we jump upon the different PTO systems, we have to understand the types of mechanical motions that wave energy converters utilize to extract energy from ocean waves. When waves interact with a floating or oscillating structure, they induce various modes of motion. These motions serve as the primary source of mechanical energy that is later converted into electricity through the PTO system. One of the most commonly utilized motion is heave motion, which refers to the vertical up and down movement of a body. Because ocean waves naturally produce significant vertical displacement, heave motion is widely used in many wave energy devices, particularly point absorbers. Another important mode is pitch motion, which is the rotational movement of a structure about a transverse horizontal axis. Long floating structures and hinged devices often exploit pitch motions to capture wave energy. The third mode is surge motion, which corresponds to the horizontal back and forth movement of a body in the direction of wave propagation. Some oscillating surge converters utilize the motion as their primary energy source. In addition to these individual motions, many modern wave energy converters utilize relative motion between two bodies. Instead of extracting energy from the motion of a single structure, the PTO is placed between two bodies that move differently under wave excitation. The relative displacement between these bodies can then be converted into useful power. Different wave energy converter concepts are designed to take advantage of different motion modes. For example, point absorbers predominantly utilize heave motion because they are generally compact floating devices that respond strongly to vertical wave excitation. On the other hand, attenuator type devices such as long articulated floating structures often utilize pitch motion and relative motion between connected segments to extract energy efficiently. Therefore, when designing a PTO system, engineers must firstly identify the dominant motion available in the wave energy converter, because the PTO configuration is directly influenced by the type of mechanical motion being harvested. Before we discuss the different types of PTO systems, it is important to understand what engineers expect from a good PTO design. A well designed or a good PTO system should have high energy conversion efficiency, ensuring that maximum amount of captured wave energy is converted into useful electrical power. Since ocean waves are naturally irregular and continuously changing, the PTO must also be capable of operating effectively under a wide range of sea conditions. Another important requirement is durability. Offshore environments are highly aggressive with constant exposure to seawater, corrosion, cyclic loading and fatigue effects. Therefore, PTO components must be robust and reliable over long operation periods. In addition, maintenance operations at offshore locations are both expensive and challenging. For this reason, modern PTO systems are designed to minimize maintenance requirements and maximize operational availability. A good PTO should also provide a relative smooth and stable electrical output despite the fluctuating nature of wave energy. Finally, it must be capable of surviving extreme sea states and storm conditions without suffering major damage. Therefore, the ideal PTO combines efficiency, reliability, durability, and survivability while operating in one of the harshest environments on the earth. With these functional requirements in mind, let us now examine the major classifications of PTO systems used in modern wave energy converters. Having understood the functional requirements of a good PTO system, let us now examine the major classifications of power takeoff systems used in energy conversion. As shown in the figure, the PTO technologies can be broadly classified into 5 categories. One is mechanical PTO systems, hydraulic PTO systems, pneumatic PTO systems, electrical PTO systems, and direct drive linear generators. The first category is mechanical PTO system. These systems are mechanical transmission elements. They use mechanical transmission elements such as gears, rack and pinion systems, crank slider arrangements, cam mechanisms, and flywheel systems to transform oscillatory motion of a wave energy converter into rotary motion, suitable for driving a generator. Mechanical PTOs are relatively simple but may experience wear and maintenance issues due to moving components. The second category is hydraulic PTO systems, which are among the most widely studied PTO technologies. In these systems, wave induced motion drives hydraulic cylinders and pumps, generating pressurized fluid. This pressurized fluid is then used to operate hydraulic motor connected to an electrical generator. Hydraulic motor here is connected to electrical generator. Hydraulic PTOs offer flexibility and energy smoothing capabilities through the use of accumulators. The third category here is pneumatic PTO systems. These systems are commonly associated with oscillating water column. Instead of liquid fluid, they use oscillating air flow generated by wave action to drive turbines, such as the well turbines and other self-rectifying turbine configurations. The fourth category here is the electrical PTO systems. Here, the mechanical motion is converted into electrical energy using conventional electrical generators. Depending on the design, permanent magnet generators, synchronous generators, or induction generators may be employed. Finally, the fifth category is direct drive linear generators. These systems eliminate intermediate mechanical transmission stages and convert linear motion directly into electrical energy through electromagnetic induction. Here also we use permanent magnet and copper wire windings or tubular linear generators and slotless linear generators. Because here fewer components are involved, direct drive systems can be potentially reduce mechanical losses and maintenance requirements. Each PTO technology has its own advantages and limitations. The selection of a suitable PTO depends on factors such as wave energy converter configuration, the power rating, efficiency requirements, and reliability considerations, maintenance strategy, and overall project economics. In this lecture, we will obtain a broad overview of these PTO categories. In the subsequent lectures, we will discuss each of these technologies in much greater detail, including their working principles, components, advantages, limitations, and practical applications. Let us now begin our discussion of the first major category of the power takeoff technologies, namely mechanical PTO systems. Mechanical PTO systems are among the easiest approaches used for wave energy conversion. The basic idea here is straightforward. The oscillatory motion generated by waves is mechanically transformed into a form that can drive a electrical generator. Several mechanical transmission mechanisms have been proposed and developed for this purpose. One common approach is the use of gear trains, which convert and amplify motion through multiple gear stages. Another widely studied mechanism is the rack and pinion mechanism, where linear motion is converted directly into rotary motion. In addition, crank slider mechanism can transform reciprocating motion into continuous rotational motion, while flywheel systems can be employed to smooth fluctuations in rotational speed and power output. The figure shown on this slide illustrates the rack and pinion based mechanical PTO system. As the floating buoy moves up and down under wave action, the rack moves undergoes a linear motion. This motion is transformed to a pinion gear, which converts the linear displacement into rotational motion. Through a series of gears, chains, and sprockets, the rotational motion is ultimately transmitted to an electrical generator. One of the major advantages of this mechanical PTO system is their relatively simplicity. Since energy is transformed directly through mechanical components, the conversion pathway is easy to understand and implement. Mechanical PTOs also provide direct motion transfer with relatively few intermediate energy conversion stages. However, these systems also have important limitations. Offshore environments subject mechanical components to continuous cyclic loading, leading to wear and fatigue and component degradation. Gears, bearings, chains, and moving joints require regular inspection and maintenance. As a result, long-term reliability can become a challenge, particularly in harsh marine environments. For these reasons, although mechanical PTO systems remain attractive due to their simplicity, researchers have increasingly explored hydraulic, pneumatic, and direct drive electrical alternatives that may offer improved reliability and energy capture performance. The work shown in this figure, reported by Chandrasekaran and Harinder, provides a good example of how a mechanical transmission and transmission mechanisms can be employed to convert wave induced motion into electrical power. In the next slide, we will examine hydraulic PTO systems, which represents one of the most widely adopted PTO technologies in modern wave energy conversion research. Let us now move on to one of the most widely researched, commonly promising PTO technologies, namely the hydraulic power take-home system. Hydraulic PTO systems are particularly attractive for wave energy applications because they can efficiently handle large forces and highly irregular motions, both of which are characteristics of ocean waves. The basic operating principle is illustrated in the schematic shown on this slide. When waves interact with a floating body, the resulting motion drives a hydraulic cylinder. Wave motion drives a hydraulic cylinder. The resulting motion drives hydraulic cylinder, then pressurizes the hydraulic fluid. This pressurized fluid is then directed through valves and hydraulic lines to a hydraulic motor. The hydraulic motor converts fluid pressure into rotational mechanical power, which is subsequently used to drive an electrical generator and produce electricity. One of the major advantages of hydraulic PTO system is their ability to incorporate hydraulic accumulators. These accumulators act as temporary energy storage devices, helping to smooth the highly fluctuating power associated with irregular ocean waves. As a result, the generator can operate under more stable conditions, improving power quality and overall system performance. Another important advantage is the excellent force transmission capability of hydraulic systems. Large wave induced loads can be transmitted efficiently through relative compact hydraulic components, making them suitable for medium and large scale wave energy converters. The photographs shown on the right side illustrate a practical implementation of a hydraulic PTO system developed and experimentally investigated by Chandrasekaran and Sricharan in the year 2020 and 2021. The upper photograph shows the floating wave energy device in a wave basin, while the lower photograph highlights the hydraulic cylinder assembly used for wave energy conversion. Despite these advantages, hydraulic PTO systems also have some limitations. Since the system relies on pressurized fluid circuits, leakage can occur if seals, hoses or valves deteriorate over time. Furthermore, hydraulic systems contain multiple components including cylinders, accumulators, valves, pumps and motors, which can increase maintenance requirements and the system complexity. Nevertheless, because of their flexibility, controllability and energy smoothing capability, hydraulic PTO systems continue to be among the most extensively studied PTO technologies in wave energy research. In fact, several well-known wave energy devices around the world have successfully employed hydraulic PTO concepts to improve energy extraction and power conditioning performance. Let us now discuss Another important category of power takeoff technologies known as pneumatic PTO systems. Unlike hydraulic PTOs, which uses pressurized liquid as the energy transfer medium, pneumatic PTO system utilize airflow to generate electricity. These systems are most commonly employed in oscillating water columns, in short called as OWC devices. The OWC is one of the oldest and most extensively researched wave energy conversion concept. The working principle is relatively simple. As waves enter and leave the partially submerged chamber of the OWC, the internal water column oscillates vertically. This oscillating water surface behaves like a piston, alternatively compressing and decompressing the air trapped above it. As a result, air is forced to flow through a, uh, back and forth through a turbine located at the top of the chamber. The turbine converts kinetic energy of the moving air into rotational mechanical energy, which is then used to drive an electrical generator. One interesting feature of pneumatic PTO system is that the airflow continuously changes changes the direction as the water column rises and falls. To overcome this challenge, special turbines known as self-rectifying turbines are used. Among these, the well turbine is the most widely studied. The well turbines has specially designed blades that allows it to rotate in the same direction regardless of the direction of the airflow. Consequently, electricity can be generated during both the inhalation and exhalation phases of the oscillating air column. The schematic shown on the right side illustrates the operating principle of an oscillating water column device where wave motion induces airflow through the turbine. The figure below shows the examples of turbine configurations typically used in pneumatic PTO systems. Pneumatic PTO systems offer several advantages. They contain relatively few moving parts in contact with seawater, reducing corrosion and maintenance issues. Furthermore, the turbine generator assembly can often be located above the waterline, simplifying inspection and servicing. However, pneumatic PTO systems may exhibit lower overall efficiency compared with some hydraulic and direct drive alternatives due to aerodynamic losses and turbine performance limitations under highly irregular sea states. Despite these challenges, oscillating water column device remain one of the most mature wave energy technologies and continue to attract significant research and commercial interest worldwide. Having examined pneumatic PTO systems, we shall now move to PTO technologies that rely directly on electrical generators for energy conversion. Pneumatic PTO technologies having discussed the pneumatic PTO technologies, in electrical PTO systems, the objective is to convert mechanical motion into electrical energy using conventional electrical generators. The most common approach is to use rotary electrical generators, where wave induced motion is first converted into rotational motion through a mechanical transmission system. The rotating shaft then drives a generator and produces electricity. Among the various generators, the technologies available, permanent magnet generators or PMGs have become particularly attractive for wave energy applications. These generators provide high efficiency, compact design and reliable performance at low rotational speeds, which are common in ocean wave environments. The fundamental operating principle behind all electrical generator is electromagnetic induction, first described by Michael Faraday. According to Faraday's law, whenever there is a relative motion between a magnetic field and an electrical conductor, a voltage is induced. In wave energy converters, this relative motion is ultimately created by the movement of waves. Therefore, regardless of whether the PTO is mechanical, hydraulic or pneumatic, the final stage of electricity generation often relies on electromagnetic induction. The key message of this slide is summarized like this: mechanical motion is directly converted into electricity using electrical PTO system. The direct conversion pathway generally results in higher energy conversion efficiency and simpler integration with electrical power systems. In the next slide, we will examine more advanced form of electrical PTO known as the direct drive linear generator, where the intermediate rotary conversion stage is completely eliminated. Unlike conventional electrical generators, which require rotational motion, a linear generator produces electricity directly from linear motion inside a chamber or a cylinder with copper windings. The basic concept here is illustrated in the figure shown on the slide. A linear generator consists of two main components, a moving component called as a translator, which carries a permanent magnets. This is a translator which moves, which carries a permanent magnets. A stationary component called as a stator. Which contains electrical copper windings. As ocean waves cause the floating body to move, the translator moves linearly relative to the stator. The relative motion changes the magnetic flux, linking the stator windings. According to Faraday's law of electromagnetic induction, this varying magnetic flux induces an electrical voltage, thereby generating electricity. Because the motion is converted directly into electrical power, there is no need of gearboxes, hydraulic circuits, turbines or other intermediate transmission systems. This provides several important advantages. First, direct drive systems have fewer moving parts, reducing mechanical wear and improving reliability. Second, the elimination of intermediate transmission stages, significantly reduces mechanical losses, allowing a large fraction of the absorbed wave energy to be converted into useful electrical power. Third, the simplified mechanical arrangement often leads to lower maintenance requirements, which is highly beneficial for offshore installations where maintenance operations are expensive. However, direct drive generators also present certain challenges. One major challenge is cost. Large quantities of permanent magnets and copper windings are typically required, increasing manufacturing expenses. Another challenge is control complexity. Ocean waves are highly irregular, causing continuously varying velocities and forces. Consequently, advanced control strategies and sophisticated power electronics are required to maximize energy capture and ensure stable electrical output. The schematic on the right side illustrates a spar type wave energy converter incorporating a linear generator as a PTO. As the float and the spar move relative to each other, the translator moves inside the generator. Producing electricity directly from wave induced motion. One more figure here below illustrates the internal arrangement of magnets and coils. These are magnets. They are called as N52 neodymium magnets. And coils. These are copper winding coils. Typically used in laboratory scale linear generator system. Today, direct drive linear generators are considered one of the most promising PTO technologies for next generation wave energy converters because of their high efficiency, compact design and reduced maintenance requirements. In the following slides, we will compare the advantages and limitations of different PTO technologies and understand how engineers select the most suitable PTO system for a particular wave energy converter. Now that we have discussed the major PTO technologies individually, let us compare them side by side. This comparison is important because no single PTO technology is universally superior. The choice of PTO depends on the wave energy converter type, power rating, operating environment, maintenance strategy, and economic considerations. Let us start with the mechanical system. Mechanical PTOs use gear, rack and pinion arrangements, clank slider mechanisms and flywheels to transfer the motion. Their main advantages are simplicity, robustness and relatively low cost. However, because they rely on moving mechanical components, wear and fatigue and maintenance becomes important concerns over long-term operation. These systems are commonly found in small wave energy devices, educational prototypes and early generation wave energy converter concepts such as Salter's duck. Moving to hydraulic PTO systems, These are among the most widely implemented PTO technologies. Hydraulic systems can amplify force and store energy temporarily using accumulators, enabling smoother power output. This makes them particularly attractive for long offshore wave energy converters. However, hydraulic systems are associated with fluid leakage, efficiency losses, and relatively complex maintenance. The well-known Pelamis wave energy converter is one of the best known examples utilizing hydraulic PTO technology. Next, we have pneumatic PTO systems. These systems are mainly used in oscillating water column devices where wave motion causes bidirectional airflow through a turbine. Pneumatic systems eliminate hydraulic fluids and have relatively simple operating principles. Their main limitation is lower overall efficiency due to airflow and turbine losses. Nevertheless, they remain highly stable, suitable for shoreline and breakwater integrated wave energy systems. The fourth category here is electrical PTO systems based on rotary generators. These systems convert mechanical motion into rotational motion and then into electricity using conventional electrical generators. Because generator technology is highly mature, these systems are reliable and well understood. However, additional components such as gearboxes and transmission systems may increase cost, complexity, and maintenance requirements. Finally, we have direct drive linear permanent magnet generators. These systems eliminate intermediate transmission stages and convert linear wave motion directly into electricity. Their major advantages include high efficiency, fewer moving parts, and no gearbox, reduced mechanical losses, and potentially lower maintenance requirements. However, they also involve higher capital costs and require sophisticated control and power electronic systems to operate effectively under highly irregular ocean waves. If we look at current research trends, there is a noticeable shift toward direct drive electrical PTO technologies because of their potential for higher efficiency and improved reliability. Nevertheless, hydraulic PTO systems continue to dominate many commercial scale prototypes because of their proven operational experience. Therefore, engineers must always balance efficiency, reliability, cost, survivability, and maintenance requirements when selecting a PTO technology. This comparative understanding provides the foundation for designing efficient and economically viable wave energy converters. Having compared different PTO technologies, it is equally important to understand what determines the efficiency of PTO system. The ultimate objective of any power takeoff system is to extract maximum possible energy from incoming waves and convert it into useful electrical power. Several factors influence this efficiency. The first factor here is mechanical losses. These losses occur due to friction in gears, bearings, shafts, chains, and other moving components. Mechanical PTO systems are particularly affected by these losses. The second factor is hydraulic losses. In hydraulic PTO systems, energy is lost through fluid friction, leakage, pressure drops, and inefficiencies in hydraulic motors and valves. The third factor here is electrical conversion losses. Generators, transformers, and power electronic converters and electronic transmission systems are never perfectly efficient. A fraction of the captured energy is always dissipated as heat. Another important factor is wave irregularity. Ocean waves are highly variable in height, period, and direction. Because of this variability, the PTO rarely operates continuously at its optimum condition. Finally, the control strategy plays a major role in energy capture. Advanced control methods such as reactive control, latching control, and model predictive control can significantly improve the amount of energy extracted from waves. Therefore, PTO design is not only about energy conversion, it is also about intelligent control and optimization. As summarized, an efficient PTO system maximizes energy capture while minimizing losses and structural loading. This balance between the performance and survivability is one of the central challenges in wave energy engineering. Now, let us look at the broader engineering challenges faced by PTO systems operating in harsh offshore environments. Although many PTO technologies have demonstrated promising performance in laboratories and prototype developments, operating in the real ocean introduces several significant engineering challenges. The first challenge here is corrosion. Marine environments are highly corrosive due to the presence of salt water, humidity, and continuous exposure to the atmosphere. PTO components must therefore be designed using corrosion resistant materials and protective coatings. The second challenge is biofouling. Marine organisms such as algae, barnacles, and shell forming species can attack and attach themselves to exposed surfaces. Over time, biofouling increases drag effects, mechanical motion, and increases maintenance requirements. Another important challenge is fatigue loading. Unlike conventional structures subjected to occasional loading, wave energy converters experience millions of loading cycles throughout their operational life. These repeated stress cycles can lead to fatigue damage and eventual component failure if not properly accounted for during design. The next challenge is extreme wave events. While PTO systems must efficiently capture energy from normal operating waves, they must also survive severe storms, hurricanes, and extreme sea states without catastrophic failure. In addition, PTO systems must operate under variable wave frequencies and amplitudes. Ocean waves are continuously changing, requiring the PTO to adapt to different operating conditions while maintaining good efficiency. Finally, there is the challenge of maintenance accessibility. Unlike land-based power systems, offshore devices are difficult and expensive to assess whether windows may be limited and maintenance vessels can significantly increase operational costs. For this reason, reliability often becomes more important than achieving the absolute highest efficiency. This idea is captured by the statement, reliability is critical for commercialization. A PTO technology can only become commercially successful if it can operate efficiently, survive harsh offshore conditions, and require minimal maintenance over long periods. In the final slide of this lecture, we will summarize the key concepts discussed and identify the major takeaways regarding PTO technologies for wave energy converters. Having discussed the major PTO technologies and their engineering characteristics, let us now look at how these systems are implemented in real wave energy converters. The first example here is the Pelamis wave energy converter shown in the upper top right. Pelamis employed a hydraulic PTO system. As waves passed along the articulated structure, relative motion occurred between adjacent sections. Hydraulic cylinders converted this motion into pressurized fluid, which then drove hydraulic motors connected to the electrical generators. Various parts of the hydraulic PTO are shown here. Pelamis became one of the world's most famous wave energy projects and demonstrated the practical viability of hydraulic PTO technology. The second example is the oscillating water column or OWC. In OWC devices, the oscillation of the water surface inside a chamber causes air to flow back and forth through a turbine. This makes OWC systems a classical example of pneumatic PTO technology. The photograph on the right side shows LIMPT OWC on the Isle of Islay in Scotland, one of the most successful shoreline wave energy projects. The third example is the point absorber represented by the Boyd type experimental device shown in the lower side, that is core power. Point absorbers commonly utilize direct drive generators or the compact PTO arrangements because their primary motion is heave or vertical moment. These devices are particularly suitable for direct conversion concepts. The central image shows a core power device. Here, a modern point absorber that combines advanced control strategies with high efficient PTO technology to improve energy capture. Finally, some wave energy converters employ mechanical linkage systems where gears, crank mechanisms or rack and pinion arrangements transfer wave motion to electrical generators. These examples clearly demonstrate that PTO selection depends strongly on device architecture and operating requirements. There is no universal PTO technology suitable for all wave energy converters. Instead, the PTO must be matched carefully to the wave energy converter's motion characteristics, power rating, maintenance requirements, and deployment environment. This practical perspective helps us understand why PTO development remains one of the most active areas of wave energy research. Wave energy technology is evolving rapidly, and several new research directions are shaping the future of PTO systems. One important trend is the development of smart PTO systems. Modern PTOs are no longer passive energy conversion devices. They increasingly incorporate sensors, real-time monitoring, and advanced controllers that continuously adjust operating conditions to maximize power extraction. The second trend is adaptive damping control. The amount of damping provided by the PTO significantly influences energy capture. Adaptive control techniques continuously modify the damping characteristics to match changing wave conditions, thereby improving efficiency. Another exciting area is artificial intelligence and machine learning. AI-based optimization techniques can predict wave conditions, optimize control parameters, and improve overall efficiency and energy capture. These approaches are becoming increasingly important as computational capabilities continue to advance. Researchers are also exploring hybrid PTO systems. Hybrid systems combine multiple energy conversion mechanisms such as hydraulic and electrical PTOs to take advantage of the strengths of each technology while reducing their individual limitations. Finally, there is growing interest in energy storage integration. Because wave energy is inherently variable, integrating batteries, supercapacitors, flywheels, or hydraulic accumulators can smooth power output and improve grid compatibility. These developments indicate that future PTO systems will be more intelligent and adaptive and integrated than current designs. As wave energy technology matures, advanced control and optimization may become just as important as the mechanical design of the PTO itself. Let us briefly summarize today's lecture. We learned that power takeoff or PTO system is the heart of the wave energy converter responsible for converting wave induced mechanical motion into electrical energy. We discussed the major PTO techniques including mechanical PTO systems, hydraulic PTO systems, pneumatic PTO systems, electrical PTO systems, direct drive linear PTO systems. Each technology has its own advantages, limitations and suitable applications. We also examined the key factors affecting PTO performance such as efficiency, reliability, survivability and maintenance requirements. Finally, we reviewed real world PTO applications and emerging trends such as smart control, AI based optimization, hybrid PTO systems and energy storage integration. The key takeaway is that the choice of PTO system plays a crucial role in determining the efficiency, reliability and commercial success of a wave energy converter. Thank you for your attention. In the next lecture, we will continue our discussion by exploring advanced PTO technologies and their practical implementation in wave energy systems. Thank you.